Permutation when all objects are not distinct object. Okay, so here we have to understand that what do we mean by this statement. Okay, so for example, this can be better understood by taking this word. Consider that we have this word banana, B-A-N-A-N-A. Okay, this word we have taken. Okay, now each letter can be considered as an object. Okay, if we consider each letter as an object, then A, and A, these three A's would be identical. So, and these two N's would also be identical. Okay, so here A is repeating 3 times and N is repeating 2 times. Okay, so objects are not distinct and also they are repeating 3 times. So this is what we mean. All the objects are not distinct, meaning to say that some objects are repeated. Okay. So if we have to form the permutation of this word banana, taking all the letters at a time, then how does the repetition of objects, or in this case letters, affect the number of permutations? Okay, so if the objects are not distinct, so we have to understand this concept that how does the repetition of the objects affect the number of permutations. So for this, what I do, I assume that B, A1, N1, A1, N1, this is A2 and this is A3 and this is N2. So what I do, I make these A's as distinct by giving them the numbers A1, A2 and A3, and I also make N, both the N's as distinct by giving them numbers N1 and N2. Okay, so these A's can arrange themselves in how many ways? They can arrange themselves in how many ways? 3 factorial ways. Because there are 3 places, okay, and in 3 places we can arrange 3 objects, that is A1, A2 and A3 in how many ways? 3 into 2 into 1, that is equal to 3 factorial ways. No problem about that. And N1 and N2 can be arranged in how many ways? 2 factorial ways. Okay. So by assuming A1, A2 and A3 as distinct, we get these many ways also. 3 factorial ways and 2 factorial ways extra. But if but all the A's are identical. Being identical, they are equivalent to only one arrangement. Okay, if we have 3 A's placed in 3 places, then if we change their places, then this is not a different arrangement. Okay, similarly N's, if we are going to change them, then it is not going to represent a different arrangement. Okay, if they are distinct, then they are going to give rise to how many arrangement? A's are going to give rise to 3 factorial arrangement and N's are going to give 2 factorial arrangement. Okay, now because the total number of arrangement is equal to how much? 6 factorial. And when is this possible? This is possible when all the letters are assumed to be distinct. Okay, on being similar, these 3 factorial arrangements would be becoming 1, so we have to divide it by 3 factorial, and 2 factorial arrangement are also going to be treated as 1, so we are going to divide it by 2 factorial. Okay, so whenever the objects are repeated and we have to form a permutation of repeated object, then the number of arrangements they can form, if they are distinct, has to be divided from the total number of arrangement to get the exact number of arrangement. Okay, so this can be understood by formula. It doesn't. This can be understood by certain example. There is no way that we can prove this result. Okay, so the logic behind is this, that if we assume them they are different, then they are going to give rise to a large number of arrangement. If they are same, then they will be equivalent to one arrangement. Okay. So the number of arrangements they are going to be producing being distinct is divided by the total number of arrangements. And here 6 factorial was obtained because we have assumed, because there are 6 letters and number of ways of arranging 6 letters in 6 places would come out to be 6 factorial. Okay, this can be done separately also. Okay. Theorem on permutation when all objects are not distinct object. Okay. So the theorem is like this. The number of permutation of n objects where p objects are of same kind and rest are different is equal to n factorial upon p factorial. Okay. So this theorem can be straight away applied in the condition in which we have n objects. All the objects are to be arranged. Okay. And only one object is repeated, or in other words we can say that p objects are same. Out of the n objects, p objects are same, identical. Okay. So then in this case the total number of arrangements would be equal to n factorial upon p factorial. By the objects are of same kind, we mean that they are identical. Okay. For example, in any word, if 2 A's are repeated, then if we interchange them, then it doesn't make any difference. Okay. So by identical we mean that if on replacing or interchanging these two with each other, then the arrangement remains the same, or the arrangement is not altered. Okay. Now we are going to consider an example. The example is like this. We have these letters A, B, A, C, A, D, A. These letters are taken. Okay. So I make a problem like this. So how many arrangement of these letters are there if all letters are taken together? Okay. So these are 7 letters. No problem about that. So if we have to calculate the number of arrangements or permutations which this is going to, these letters are going to produce, this will be equal to 7 factorial, and because A is repeated 4 times, so this will be equal to 7 factorial upon 4 factorial. Okay, so this is how we are going to apply this formula, or this is a condition in which we can apply this formula. Okay, theorem on permutations when P1 objects are of one kind, P2 objects are of second kind, Pk objects are of kth kind, and rest, if any, are all different kind. So this theorem is the extension of the previous theorem, and in this the repetition of more than one object is there. Okay, so this theorem clearly states that the number of permutation of n objects. Okay, so we have n objects and all the n objects are to be taken to be arranged. P1 objects are of one kind, that is we have P1 identical objects are of one kind, P2 identical objects are of second kind, and Pk identical objects are of kth kind, and rest, if any, are all of different kind. Then in this case the total number of arrangements would be equal to n factorial upon P1 factorial into P2 factorial and so on up to Pk factorial. How? Okay, so how we are going to apply this in a practical problem? It is like this. Consider that we have these letters A, A, B, 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 C, 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 C. Okay, and E, E. Okay, so we have in all how many letters? These are 5, 5, 10 and 1, 11. So these are total 11 letters. The total number of arrangement of these 11 letters would be equal to 11 factorial upon 2 factorial. Here we have written 2 factorial because A is repeated 2 times. Again we are going to divide it by 3 factorial because B is repeated 3 times. 4 factorial because C is repeated 4 times, and 2 factorial again because E is repeated 2 times. So this is how we are going to apply this formula or theorem in a to our practical problems. Okay.